Next topic, AC circuit containing a resistor, an inductor and a capacitor in series RLC circuit. Consider a circuit containing a resistor of resistance R, an inductor of inductance L, a capacitors of capacitance C connected across alternate voltage sources V. V is produced voltage. The V is equal to Vm sin omega t. Now, let I, the flowing of the current, each and every component, the final be the resulting circuit current is a circuit at the instance as a result of the voltage dropped across to resistance, inductor, capacitor. We know that the voltage across the R is equal to VR in the space with I. The voltage drop across the inductor L into VL, the leads I by pi by 2. And the voltage drop across to C, capacitor V into VC, lags I by pi by 2. The phasor diagram draw with a current in refer phasor. The phasor diagram, the as usual, the two component, the along the x-axis considered to current, along the y-axis considered to voltage. Now, the flowing of the current or resistance of flowing of the current OA vector. This is a considered to current I. OB vector you consider to voltage VL. OC vector you consider to voltage resistance capacitance of the voltage. This diagram you fix it to slightly position of the spacer diagram. The length of the phasor or here the induce of the resistance, the current OA vector is equals VR, voltage of resistance, that is equal maximum current into resistance. OB vector is equals IM into XL, maximum current into impedance of the inductor. OC vector is equal to IM into XC, inductance capacity. A circuit is either effective inductive or capacitive or resistive. That it depends on the values of VL and VC. Let us assume that VL greater than VC, so that net voltage drop across L and C, inductance and capacitors combinations is VL minus VC. It is a reduce the current, which is represented by the spacer AD. The spacer diagram. Where is the AD? This is the AD. OA vector, OB vector, OC vector, OD vector is the resultant vector. Consider voltages. Voltage vector. Here, by using a parallelogram law, this is using take the parallelogram. Here's the half of the diagonal at OA vector. Given the result voltage V and VR, given the voltage V, what is a VR? And VC and VL. It is a length OA is equal to maximum voltage. OE, the resultant voltage OE is equal to VM, maximum voltage equal. You want to this diagonal OA vector is equal, take a Pythagoras theorem. You take the first one of the right angle triangle. I want to this side VM squared is equal the sum of the other square of the both side. VR squared plus VL minus VC squared. Here, VM squared is equal to VR squared plus VL minus VC squared. What is the values of maximum square? You want the only VM. The VM take the root this side. The root of VR square plus VL minus VC squared. Now, applying to the values of VR. The values of VR, resistance of voltage IMR whole squared plus inductance voltage IMXL minus of capacitance voltage IMXC whole square. That is equal, take the maximum current outside. IM root of R square plus XL minus XC whole square. What is the IM? The maximum current, the applied to the Ohm's law. Ohm's law given the Im maximum current is equal to voltage divided by resistance. Now you substitutions values Im Vm divided by R, that is the root of R square plus XL minus XC whole square, equations number 2. What is the Im? Im means Vm by Z. What is the Z? Z means this is called a impedance of the circuit. Im is equal to Vm divided Z. Z is equal to root of R square plus XL minus XC whole square, equation number 3. Z is called impedance of the circuit, which refer to the effective portions of the circuit current by the series RLC circuit. The current series RLC circuit voltage triangular and impedance triangular. Take the spacer diagram. Two diagram you take. This first one is a spacer diagram of voltage diagram. Another one is a impedance diagram. Impedance diagram means current diagram. You take the voltage of triangular and the impedance triangular are given from the spacer diagram. The space angle between voltage and current is found out from the following relation. The following relations, tan phi is equal to tan is equal opposite side divided by adjacent side. The tan phi is equal to opposite side VL minus VC divided by VR. That is equal to voltage diagram. Now here's take the another triangle, impedance triangular. Tan phi is equal to same opposite side divided by adjacent side. Opposite side XL minus XC divided by R. This is equation number 4. Now this is a spacer diagram, space angle between the out of the following relations. Now the special cases. What is the special cases? The first is cases of if XL greater than XC, that is equal XL minus XC, is a positive and space angle pi is also positive. It means that applied voltage leads the current by pi and lags behind the voltage. This is a current is a inductive. The current inductive, the voltage V is equal to Vm sin omega t, I is equal to Im sin of omega t minus pi. The second case, if XL less than XC, that is XL minus XC is a negative and pi is also negative. Therefore, current leads voltage by the pi and circuit is a capacitive. The same voltage V is equal to Vm sin omega t. No changes of voltage, only a difference of the current. I is equal to Im sin omega pi plus pi, omega t plus pi. The third case, the XL is equal to XC. If XL is equal to XC, pi is 0. Therefore, current and voltage are the same space and circuit, resistive. V is equal to Vm sin omega t. V is equal to Vm sin omega t. I is equal to Im sin omega t.